Hello, everybody. Good morning. I'm Jordi Baylina. I'm the technical lead at Polygon zkVM. And today I want to explain a little bit the work that we are doing in the aggregation layer. Aggregation layer is part of the Polygon 2.0 ecosystem. Is the part that mainly interconnects different chains. As you know, the Polygon 2.0 is, I like to call it a constellation of chains. The first one is the Polygon zkVM, but here other networks are going to be connected. I mean, Polygon Maiden, the POS is going to be connected also here to the Polygon 2.0. But here we're also connecting all the CDKs. CDKs, this can be private chains, public chains. You can build your own chain. I mean, you can, and the idea is all this change needs to be connected, and they will share the same liquidity. And another point here is the composability between chains. So the idea is that from one chain, you can have a smart contract that maybe is calling another smart contract in another chain, and then coming back and transferring values between one chain and the other. And ideally, this should be done fast in a way that from the user perspective, it should be seen everything like as a single network. Okay, and for doing this, the main technology that enables this is the ZK technology. So this, of course, another way to see this is like I like to talk about the similar about processors. I mean, here there is like two ways to scaling processors. One thing is doing processors faster, but the other is setting more cores as a processor. So of course, each chain, there is a technology to make this chain faster, but at some point there is some limitation, and then the way to scale is having many processors, in this case many chains that connect and that communicate one with the other. Here, of course, we are talking about a trustless, a trustless bridge in a thing that it doesn't depend on third parties and things like that. Okay, so. Yeah, this is the main advantage. I think that from the user perspective, this can be super interesting. I mean, imagine, for example, I don't know, a private network of some corporation talking maybe with another insurance company and doing some swap in Uniswap chain, or just there's composability between chains. This, here we are enabling for the people that's out in the space. This reminds me a lot at 2015 or something like that, when we were talking in Ethereum about sharding. At that point, we didn't distinguish between data availability and everything. I mean, shards were just execution environments at that point. And we start talking about this cross-chain, these asynchronous calls, cross-chain communication, or in this case was cross-shard communication on that. This is the equivalent that we have right now. So now it's time actually to put all that theory that appears in 2015, 2016, and put that in practice. Okay. So the first step is what we have. I mean, this is the LXLY bridge. Okay. So in order to understand how this aggregation layer works, we need to understand how the bridge works. And what's the idea of the bridge? Okay, so let me explain briefly how a bridge works. Okay, if you have different chains, and you can consider L1 as another chain, maybe it's a special chain, but at the end it's another chain. Every time that a chain wants to transfer funds to another chain, actually what we call log. We have a kind of a database, or if you want a Merkle tree of exits of that chain. I mean, we call this local exit route. Okay, so you have a chain. Every time that we do the transfer to another chain, we add a leaf to this tree. Okay, and in this tree is an append-only tree, so you see only the different the additions to those trees. Okay, and here the idea is that we collect this root of this local exit route. Okay, in mainnet, and we create another root of all the trees. So it's a tree that aggregates all the trees of all the chain, and we call this tree the global exit route. And this global exit route is actually broadcast to all the networks. So the idea is how it works. I mean, you send funds to another chain. You send your funds to a smart contract. This smart contract actually updates the local exit tree. This local exit tree, when the proof is generated, it's inserted in the global exit tree. The global exit tree, it's sent to the other chain. The other chain already have this global exit tree, and then in the other chain you can claim those funds because you can prove that the exit in one side is in the global exit tree. And in general, you also mark that this, in order to not double spend or not do that, so that you can only claim once, you mark that as a claim. Okay, but see, yeah. This is very much how the local exit tree would look like. Okay, this is the kind of the leaves that you can see in there. Okay. So, I mean, this is actually what's running. I mean, we already have some private chains connected to the bridge since the last week, and but this is relatively slow. Why? Because, well, when you do a transfer, the other chain cannot start using the funds until it's sure that this local exit tree is propagated to the global exit tree, and this global exit tree is actually included in the state. And for that, I mean, this is a slow, but because I mean, the idea is one chain. When you're sending some funds from chain A to chain B, well, you need the chain A needs to generate the proof and publish this proof on layer 1. At this point, then you are sure that this global exit route is updated, and then you can use it in the other chain. Generating a proof currently, it's a process that takes a couple of minutes. This can be reduced. I think that can be reduced to a few seconds with technology. I mean, with improvement of the ZK technology that are coming. But in any case, there is this L1 transaction needs to happen, and the chain needs to publish this transaction. Okay, so this is the first approach. This is what it is right now. It's good because we can communicate different chains, and this is the first stage. But we can do it better. Okay, so what's the next improvement? Okay, and this is not ready yet, but it's almost ready. We are auditing the smart contracts. The idea is that in the CDKs in Polygon, instead of each chain creating their own proof and publishing their own proof and paying the cost of the proof, the idea is that one proof rules it all. I mean, the idea is take all the proofs of all the chains and aggregate all the proof to a single proof. Okay, and this proof, and then when you publish this proof, is a proof that's proving all the chains. Okay, so it will not earn directly speed because it's exactly the same. You need to prove, but the idea is that the cost of the proof is going to be much more smaller, and because this proof is aggregated to all the chains, we can send this proof more frequently. So we can send maybe this proof once every minute, 2 minutes, or every 3 minutes, because it's a proof that's common to all the chains. Of course, the chains can do the proof individually if they want, but if they send the proof to this aggregator and then this proof is aggregated, then this is going to go. I mean, we will guarantee that this proof is more peaceful. And this proof is. It's like a clock. I mean, this proof is what actually triggers the transfers. Okay, because in this proof is when we take the global exit route and we send it and broadcast to the other chains. And this is like a clock for all these transfers. Okay, but for this we still need to wait for the proof generation and the clock. Okay, so what's the next stage? Okay, and this is mainly the core of the aggregation layer in the future. Okay, the next stage is the idea is to have a blockchain or something similar that's a kind of a coordination blockchain. Okay, and the idea here is that the chains can commit to a given state. Okay, so and okay, they commit to this when the chain commit to one state, the chain cannot change this state. So the other chains now have the warranty that this state will not be modified, and the other chains can start using this in the local exit route, or the state of this change can start using that chain. What are the conditions that the other chains what conditions are required for the other chains to accept this? Well, the first is, of course, that the state is committed, and the second is that the second chain is able to generate the proof that goes to this state. So actually, it's not necessary to generate the proof. If another chain is able to generate the proof, maybe because it's following the other chain, they can start using the other chain. Why? Because the state of the other chain is committed, and if the other chain doesn't publish the proof, you can always build the proof. So the other chain can build the proof. So then this guarantees that I'm not going to be locked. So what's the problem? I mean, what's the bigger problem? Let's explain it in a different way. Okay? So imagine that we have a chain A and chain B. Chain A commits to the state 1, to A1. And then chain B commits to B1, okay, but the chain B requires A1 to. I mean, it depends on A1, okay. So it's using the local exit route of A1, okay. So if the state A1 is reorg or it doesn't change, then B would be locked for that. So when chain B decides to include A1 to depend on A1, chain B needs to have the warranty that's able to prove the A1, and that A1 have the warranty that the chain A will go to the exact state route that the chain A1. Okay, so and this chain, of course, you can commit to different chains. Later on, you can prove the different states, and the proof you see here that there is a kind of a dependency tree. Between chains. I mean, maybe the state A1 depends, so the state C1, for example, depend on B1, but the B1 depends on A1. Here there is if you can see a graph of dependencies. So the state actually, the final state becomes only valid when all the dependencies are solved. Okay, and this can be computed dynamically and proved dynamically. At this chain is going to be also a kind of a checkpoint, so points where you will take this state, and the aggregated proof will be computed. It will take all this individual proof, and this aggregated proof will be computed, and then send it to layer 1 just to consolidate the state. And this can be done, again, once per 1 minute, 2 minutes, 3 minutes, or whatever. But the cool thing here is that the cross-chain communication can be solved really fast. I mean, here we are talking about seconds. If this aggregation chain has a finality of 2-3 seconds, that means that in 10 seconds you can do a full composability between different chains. Okay? So this is this is very much the core of the aggregation layer. Here, I mean, there is a lot of details, I mean, about these dependencies, the proving, the aggregation of the proof of all this. But this is the main idea, okay? And from the user perspective, I think it's interesting to see that how we are solving this fast intercommunication layer in a trusted manner. Okay. Also, this chain can be used. This chain also can be used also to decentralize the prover. I mean, because this proof, anybody should be able to generate the proof. And in this chain, we can create all the cryptoeconomics for the proof generation. So that instead of being a central server that's generating all the proof, different chains or different actors can generate the proof and get reward for that. And this is the chain that will coordinate the proof aggregation of this. Okay. And just to finalize, I'm a little bit changing a little bit here. I just, as responsible of the ZKVM team, here I want to explain the roadmap. Of course, there's no strong commitment, but this is, I think, it's good in the conference to explain what we are doing inside the team, and this is, and what you can expect in the upcoming month. Okay. Right now we are. Fully working in the EIP 4844. 4844, I mean, it's for data availability. It's going to be a super important EIP. This is going to be enabled next month in the mainnet. Okay, and so we are working, and we expect to already be using EIP 4844 at the beginning of May. Okay. And then we will work with data compression. Okay, so these are the big things on that. In parallel, we're also working actively in the Polygon integration. So this will increase a lot the performance of the zkVM because the main client is going to be Polygon. Here is the RPC and the sequencer that we're working a lot. And then in parallel, we're also working in the technology in the VATCOPS PIL2. This will allow us to remove the counters. I mean, this is a ZK counters. That's a specific thing of the type 2's rollups. But I mean, this is most of the users should not care about. But there are some DeFi applications that currently it's a little bit difficult to handle that, and the idea is with VATCOPS to remove all these counters and also increasing the performance of the prover. We expect, I mean, we don't have current numbers but we expect that 2x, 3x improvement on the proof generation will happen in the VATCOPS. Data compression, again, in the data compression, we expect that the cost of the full zkVM should be something like between 5x and 7x compression, and this is going to be very much the cost. In parallel, right now, as I mentioned before, we are onboarding the CDKs. The first networks are already live on mainnet, and we expect to in the next weeks, a month, to start onboarding different CDKs. Different chains. I think here, even from the business perspective, it's a super interesting opportunity. The CDK, it's a sovereign chain. I mean, they can have their own token. They can get all the fees. There is a lot of new opportunities for the new reward. I mean, new monetization models that can happen because, I mean, if it's a centralized sequencer, you can get all the fees. You can centralize, decentralize, going to Validium to no Validium. So here, the vision here is that all the dApps, instead of having to create their own layer 1, that's what they were doing, recently. The idea is that they can just run a layer 2, their own network. And that's going to be much easier, and they can focus in the specific application. This is a concept of dApp chains, or there is a lot of opportunities here on the CDK worlds. Okay, and of course we are also starting to work on this aggregation layer. What I presented here, the aggregation layer V2. I mean, this aggregation of the proof aggregation of the different circuits. This, I would say that the proofs and the proofs and the smart contracts, they are done. So this probably we are auditing at that phase. So I hope that in 1 month, 2 months at most, they're going to be available, and we are start working hard in this aggregation layer in the V3 in this chain to do this coordination between proof and actually go to the few seconds cross-chain composability. Okay. And that's very much what I wanted to explain. Thank you very much for listening to me.